When you think about engineering a skyscraper for an earthquake, there's this fundamental challenge.
Right, the big trade-off.
Do you build a fortress, something so stiff it just resists the
Or
force?
do you build something more like a reed,
Yeah.
flexible enough to absorb the energy and just roll with it?
You usually have to pick one. But we're diving into this 2026 paper by Abdul Rida and his colleagues that, well, it challenges that whole idea.
Their proposal is a hybrid bracing system.
And they're basically asking, why can't we have both?
And this wasn't just a theory. They tested it with simulations using some really intense historical data.
The worst case scenarios, really. El Centro, Loma Prieta, and the Kobe earthquake.
Yeah. So to really get what they accomplished, we should probably look at what engineers are already using.
Okay, so the current toolkit. There are two main methods. First, you've got concentric braced frames, the CBFs.
That's the big steel X you see on the outside of buildings.
Yeah.
That's the fortress approach. Pure stiffness.
It just fights the movement. Then you have friction dampers.
And those work on a totally different principle.
Yeah, they're basically plates designed to slide against each other. They turn the building's motion into heat.
Like brake pads on a car. One system resists the energy, the other one dissipates it.
So this is where the study gets really interesting. I was digging into their simulation for a 15-story building.
Under the Kobe conditions.
Exactly. And common sense tells you, add the big steel braces, you get a safer building.
But intuition can be a little dangerous in this field.
It was dead wrong. The study actually found that adding those standard braces increased the building's sway.
By a lot.
By over 42%, compared to a building with no braces at all.
That is a massive, massive failure. It's a phenomenon we call dynamic amplification.
Right, because in making the building stiffer, they accidentally changed its natural frequency.
And it just happened to match the ground motion of the Kobe quake almost perfectly.
They turned the skyscraper into a giant tuning fork.
And that resonance is what tears a building apart. So just adding stiffness, it's not the answer.
Which brings us to their solution, the hybrid bracing system.
It's such a clever synthesis.
Yeah.
They decided to physically integrate the two methods.
Yeah, they put the friction damper inside the concentric brace.
So the brace still provides that day-to-day rigidity you need for, say, wind load.
So the building doesn't sway in a breeze, but the damper inside, it acts like a fuse.
For sure. When the big earthquake hits, the brace itself doesn't just buckle and fail. The internal damper slides.
It soaks up the energy. You get the stiffness and the damping.
The best of both worlds.
Yeah.
And the performance data they got was pretty incredible.
It really was. For the smaller buildings, the 5-story models, the hybrid system just dominated.
It's a clear winner.
In that same Kobe simulation, it cut the roof displacement by 59.1%.
Almost 60% less movement. That's the difference between standing and falling. But I was more interested in the tall one.
The 15-story building, the one that failed with the traditional braces. The hybrid system completely solved the resonance problem. Because the dampers were bleeding off energy, that amplification never happened.
It breaks the tuning fork effect.
Yeah. With the El Centro data, it dropped the building's drift by over 48%. You get stability without the catastrophic side effects.
And there's another layer here that goes beyond just survival. It's called functional recovery.
The economics of the aftermath, right?
Exactly. What happens the day after?
In a normal braced building, those steel beams are sacrificial. They bend and buckle to save the structure.
So the building might still be standing, but it's a total loss. The frame is shot.
With the hybrid system, all that damage gets focused on the friction dampers.
Which are designed to be replaced.
So you don't tear the building down, you just go in and replace the dampers.
It's the difference between your car being totaled in an accident versus just needing a new set of brakes.
That's a perfect analogy. It changes the goal from, did the building collapse, to, can we reopen next week?
A huge difference.
So, if we have a system that can reduce seismic impact by up to 60%, that prevents these resonance failures and makes buildings way cheaper to repair.
Yeah. The logical question is,
why aren't we just building everything this way? Why are we still just welding X braces onto buildings in seismic zones?
well, inertia is a powerful force in any industry.
Yeah.
It's often easier and initially cheaper to build what we already know.
So is the industry prioritizing the ease of initial construction over real long-term resilience?
That's the provocative question, isn't it?
Something to think about next time you're looking up at a skyline. Thanks for diving in with us.